Okay, so looking at aromatic compounds. So aromatic compounds are an enormous group of chemicals based on the benzene ring. And benzene is a colourless liquid with the chemical formula C6H6. So the number of hydrogens is pretty low in comparison to most other hydrocarbons. So what I'm going to do is draw a diagram showing what benzene looks like. There's a couple of different ways that we can represent benzene, and then I'm going to do a kind of larger electron sharing diagram so we can see exactly what's happening with benzene. So I will start with the larger diagram, and then I'll do the kind of ways that we would generally represent benzene beside it. So for this diagram, we've got 6 carbon atoms that I'm going to draw in a kind of hexagon shape. Now I'm going to draw the kind of petal diagrams showing how all of the bonds are made in a benzene ring. Now I will make sure that you've got time to copy this in. Right, so each of those orbitals that I have drawn would have 1 electron in them. So anytime there's an overlap, I'll be going in and drawing 2 electrons. 1 from each of the carbons. Like so. So that's our 6 carbons, and you can see they're arranged in a hexagon. And each of the carbons is bonded to 1 hydrogen on the outside of the hexagon. So I'm just going to go ahead and draw those 6 hydrogens in. So what you can see is that we've got our 6 carbons and our 6 hydrogens, but there is also a little area in the middle of the carbons that has an unpaired electron. Now, we actually end up with an unpaired electron in our carbon, or in our benzene, and we call that a ring of delocalized electrons because all of the delocalized electrons, or all of the electrons from the 6 carbons, form a ring in the middle of the molecule. And that ring of delocalized electrons, because those electrons can all move between the carbons, so delocalized again just meaning free to move, so they're free to move within that ring, and that ring is what gives benzene its stability, because benzene is a pretty stable molecule by all accounts, particularly since each of the carbons in benzene technically only makes 3 bonds, which should make it very, very reactive, but it's not because of that ring of delocalized electrons. Now, we would generally never draw benzene like that because obviously it's a bit much. So benzene would be drawn in either of the following ways. So we can draw benzene like this. Or we can just make it even more simple and draw benzene like that. Okay. You will, if you look benzene up online or look in particular textbooks, you will very, very often see benzene drawn like this. But that's a pretty terrible representation of benzene because it makes it look like the benzene molecule has 3 double bonds. It doesn't. Benzene does not decolorize bromine water, therefore it does not have carbon-to-carbon double bonds, therefore that representation is pretty garbage. So we wouldn't want to use that representation. There are times in university chemistry where you will draw benzene rings that look like that, and there'll be a reason why we draw benzene rings that look like that, but that's way beyond what we need to know for advanced higher chemistry. So for advanced higher, I highly recommend that we look at benzene with the ring in the middle rather than the double bonds. So I'll give you a couple of minutes just to draw that diagram in, and then we'll go on and talk a wee bit more about the benzene. Okay, so we're now going to talk about some of the key features of benzene. So in benzene, each carbon atom is sp2 hybridized. So every carbon atom forms 3 sigma bonds. So of those 3 sigma bonds, you've got 2 sigma bonds with the 2 neighbouring carbon atoms and 1 sigma bond with the hydrogen atom that it's bonded to. So a very common multiple choice question, what is the hybridization, or what's the hybridization for the carbon atoms in a molecule of benzene, or even just straightforward in the short answer questions, what type of hybridization is there with the carbon atoms in a benzene molecule? So that gets asked pretty commonly. Now it says the remaining orbital on every carbon atom is a p orbital, and the p orbitals overlap with the neighbouring carbon atoms, forming a pi molecular orbital. The 6 electrons in the pi orbitals are not tied to any one carbon atom, but are shared equally by all 6 carbon atoms. These electrons are said to be delocalized and are represented by a ring in the middle of the hexagon. So that's the ring that I showed you in the middle of the molecule there. Okay, and it's the presence of this ring of delocalized electrons that gives stability to the benzene ring. So if you're asked what gives a benzene ring its stability, the answer is the ring of delocalized electrons. Okay, so what we've got here is just another little example, sort of showing maybe a slightly better representation of what the electrons look like in that kind of p molecular orbital. So in total, benzene contains 12 sigma bonds and 1 pi bond. That's the interesting bit. It's just 1 pi bond, one very large circular pi bond. And it's a planar molecule, which means if you could hold it, it would sit flat in the palm of your hand or sit flat on like a desk or a bench or something. Okay, so it's planar. I would say another really common question, particularly in multiple choice, would be like, which of the following statements is true about benzene, or which of the following statements is not true about benzene? And quite often it's a planar molecule is one of the four options. So obviously it's a planar molecule is true. So depending on the question, that may or may not be your correct answer. Okay, so we're now on to look at reactions of aromatic compounds. So as it does not contain any multiple bonds, benzene cannot undergo addition reactions. It can, however, undergo electrophilic substitution reactions. Okay, so that's not nucleophilic substitution reactions where we used a nucleophile and substituted that with an atom. These are electrophilic substitution reactions. And it's literally the only reaction that benzene undergoes. So if you've got a question and you've got a reaction happening on a benzene ring, generally it's going to be an electrophilic substitution if the reaction is taking place with the carbons on the benzene ring. So the presence of the delocalized electrons in the benzene ring makes it susceptible to attack by electrophiles. Now, just as a wee reminder, electrophiles are electron deficient or positively charged ions. So I'm just going to write that in, just in case you want a wee reminder. So they are electron deficient or positively charged, electron deficient molecules or positively charged ions. And the fact that electrophiles attack the benzene ring in this reaction is rare. It's usually nucleophiles that will attack. So, on to electrophilic substitution reactions specifically. There are four main types of electrophilic substitution reactions. In each of the reactions, an electrophile is synthesized by the reagents involved in the reaction, and this synthesized electrophile then attacks the benzene ring and takes the place of a hydrogen atom. Okay, so every carbon atom in a benzene ring has one hydrogen attached to it. So every carbon can only undergo one electrophilic substitution reaction, because once that hydrogen's been substituted, then there's not another hydrogen to substitute. So we're going to go over the four types of electrophilic substitution reactions. These get asked a lot, like they really, really do. The amount of times these questions are asked is very, very high. Okay, so we'll talk through the four types and we'll do like a little example. So the first type is halogenation. Okay, now when we do halogenation, it's usually with chlorine or bromine. We don't tend to use fluorine or iodine in these reactions. Now the first step is to synthesize the electrophile. So what I'm going to do is just write out the reagents that we would use and then show you the diagram or the kind of formula for the electrophile. We don't need to know the exact chemistry behind how the electrophile is formed. We just need to know what the electrophile looks like and what chemicals we use to make the electrophile. So for a halogenation reaction, we will use our halogen. So I'm kind of going to split this into two. So for chlorine and for bromine, because we do need to know both. So for chlorine, we would of course use chlorine, and we would use iron 3 chloride. Okay, now in this reaction, the iron 3 chloride is acting as a catalyst. And what we will have in that reaction is the production of a positively charged chloride ion or chlorine ion. And that is our electrophile. I'm not going to write in the other parts of this reaction because we don't need to know them and they can be quite complex. So we just need to know what the electrophile looks like. So it's a Cl+, and we need to know that we would use chlorine and an iron 3 chloride catalyst to do that. Then we'll look at for bromine. Not surprisingly, we would use Br2. And then rather than use iron 3 chloride, we would use iron 3 bromide. And that would be our catalyst again. And rather than synthesizing a Cl+, it's a Br+ electrophile. Like so. So what I'm going to do is just take one of those and show what the electrophilic substitution looks like. So I'm going to take my benzene ring. I'm going to pop the hydrogens on it. Just makes sense to see the hydrogens since one of them is going to be getting substituted. We will do the reaction. So for this one, I'll use the chlorine and the iron chloride. And you will substitute any hydrogen. There's no rule as to which hydrogen gets substituted. You can literally substitute any hydrogen that you like. So I'm just going to do that one there, like so. Okay, so that's our halogenation, either with chlorine or with bromine. Right, so the next type of electrophilic substitution we're going to look at is an alkylation. Now, an alkylation is basically just putting an alkyl group onto the benzene ring. And as a reminder, alkyl groups are things like CH3, C2H5, C3H7, and are quite often represented by the letter R when we're looking at synthesis and things. So, when we are synthesizing our electrophile, we would use a haloalkane that has the alkyl group that we want to substitute. So if we are trying to substitute on a CH3, we would use something like chloromethane. If we want to substitute on a C2H5, we would use chloroethane, and so on and so forth. Okay, so what I'm going to do for this is I'm going to use the letter R to represent any alkyl group, because it really doesn't matter which one we're looking at in any kind of general example. Of course, if you're given a specific example, then you would have to know whether you're using like a chloromethane or chloroethane. And we react that with an aluminium chloride catalyst, AlCl3. And what we'll get in that reaction is a positively charged alkyl electrophile. And what I'll do just to try and kind of tie this all together is I'm just going to highlight that kind of part that would be the R group. So in yellow, you could substitute in like CH3, C2H5 for the letter R. So we'll look at an actual example. So for this one, let's do a substitution with a methyl. So that means we're going to want to use CH3Cl with the aluminium chloride catalyst. And we are going to substitute on the CH3 plus that would be generated in this reaction. Again, substitute it for any of the hydrogens you like. I'm going to substitute it for that one there. Okay, so for part 3, we've got nitration. So to synthesize the electrophile here, we use a mixture of nitric acid and sulfuric acid. And that will produce the NO2 plus electrophile. And then it's simply just a case of substituting that NO2 for a hydrogen atom. Like so. And then we'll do our final example, and then I'll leave this slide up or this page up just for a couple minutes to make sure that you've had time to copy anything down as well. So I'll leave this up here so you can kind of see everything, and then we'll go on to our final example in just a minute. Okay, so let's go on to our fourth example here. So we've got a sulfonation, which is probably the most obscure and awkward of the three of them. So what we have in the synthesizing of the electrophile for a sulfonation is we would use concentrated sulfuric acid, and that will produce an HSO3 positively charged ion, which is our electrophile. And then again, it's just a case of substituting the electrophile on in place. Like so. right, so that is us finished with the work on aromatics. There are a couple of pages left of the booklet, but the pages that are left are kind of like a summary and kind of bringing everything in the booklet together, like all of your different types of reactions and how you go from like, you know, an alkene to an alcohol to an ester, or how you would go from a haloalkane to a nitrile to a carboxylic acid and all that kind of thing. So just kind of bringing all of that information together. So what my plan is on Monday, I will be putting the past paper questions for the synthesis topic online. Now, there are 102 marks of questions for synthesis from like the same amount of past papers that I've been looking at for all of your other questions. So they go heavy on synthesis in exams. So I'm going to be giving you the 3 weeks that we'll be doing blended learning. So from week beginning the 15th, so from Monday right the way through until the 1st of April, which is the day we stop for the spring break, I'm going to give you that time at home to do the organic synthesis past paper questions. Next week, I see one half of the class on Tuesday and I see the other half of the class on Thursday. So what I'm going to do is finish off the organic chemistry booklet with one half of the class on Tuesday and the other half of the class on Thursday, so that the booklet's finished, and that will also give you an opportunity to ask some questions and things on the synthesis topic. And then for the other 2 weeks, we will be starting to look at experimental work and calculations involved with experimental work, and kind of just getting some experience of actually doing some of the experiments from the Unit 3 stuff that you could be asked about in the exam. So really just kind of looking at that kind of stuff as well. I will also be trying to help you guys as much as possible with the organic synthesis past paper questions. So if I can, I'll try and run a couple of drop-ins. Whenever we can, we'll kind of figure it out. I'll try and maybe run some drop-ins and we'll just kind of see how it goes from there. So if you, I'll stop the recording now.